Okay, so today we are going to be talking about hypothesis testing. So I've told us a few times now, there's two big processes that you're going to learn second semester. The first one we've already learned, confidence intervals. Today we're going to learn hypothesis tests. We're going to talk about what is a hypothesis test and some of the background vocabulary. We're going to do that by doing an activity and then taking a little bit of notes after that. This is what we talked about last time. So we took a look at an example. We expected 17% of CEOs to be born in June and July, but when we took a sample, it was smaller. And so we talked about this idea that we need to figure out how likely would it be to get this sample proportion from that population. And we say the way that we would do that is we would do a simulation and figure out how likely is that sample given the population. That's what we're going to do today, is take a look at an example like that. So here's the example. Now, we don't know these people, but just go with me. You guys all have this open? Yeah? Okay, Mrs. Gallus claims that she's an 80% free throw shooter, but Mr. Wilcox believes she's not actually that good. So to prove her skills, she shoots 50 free throws, and she makes 32 of the shots. I'm going to do the top part with you. So we're going to do the top part together, and then you all are going to jump in here at number 3. So our population is going to be all possible free throws. By Mrs. Gallus. Our sample, though, is the 50 free throws she actually shot. Okay, for parameter and statistic, I want a statistical term. I don't just want numbers. In terms of parameter and statistic, what are we measuring? A proportion. So 80% we can write as a proportion. That 32 out of 50 we can write as a proportion. So our parameter, P, is going to be the true, or we can also say population proportion of free throws that she makes. And it's important we say makes. We've talked about you can't write in past tense because you're not going to get credit for it. Our statistic then, our P hat, is the 32 out of 50, or 0.64 of the free throws that she made. Okay, so she claims that she makes 80% of the free throws. When she shoots 50 times, she only makes 64%. What are the two possible reasons why she would only make 64% of the shots? We've talked about this. Give me one of them.
Sample variability.
Right. She really is an 80% free throw shooter, and she just happened to have a bad day. So that would be her claim. So Mrs. G really is an 80% free throw shooter. Like we said, she just had a bad day. In terms of words, this is sampling variability. What is the other possibility? Oliver? She's not, and specifically, she's less than an 80% free throw shooter. So that is what Mr. Wilcox is claiming. Mrs. G is less than an 80% free throw shooter. Okay, so here's where the stats part of this comes in. We are testing something about P. We want to know the population proportion, or the true proportion of all the shots. And so we need to figure out how do we put these two explanations in terms of P so that we can actually test them. Well, what we are going to assume, if you've watched the video, you've seen this symbol. One of the videos, you had all 3 of them. That is the null hypothesis. So what we are going to assume is that she is, in fact, an 80% free throw shooter. Has to be written as a decimal, not as a percent. So again, this is called the null hypothesis. So then what we're going to look for evidence for, HA, our alternative hypothesis, is we are going to look for evidence that she is less than an 80% free throw shooter. This is called the alternative hypothesis. We're going to write some more on this in a few minutes. Your null is always going to be a statement of equality. And so what we're going to be going on and figuring out is, what is the likelihood that she would shoot 64% if she really is an 80% free throw shooter? So that's where we're going to do our simulation. Questions before we keep going? Okay. To test Mrs. Gallus's claim, we are going to assume that she is the 80% free throw shooter and examine the probability that she would make 32 out of 50 shots purely by chance. Okay, it says use the spinner provided. We don't have a spinner, so we are going to use a random number generator. That's what you're going to do right now. So let's do this together. If we use a random number generator, what digits do we want to use? And then we have to make it so that 80% of them represent she's a free throw, she makes the free throw, 20% she doesn't. So you all tell me, what digits do you want to use? What did we come up with? What digits do we want to use? Because remember, on a random number generator, we can set the lower bound and the upper bound. So what do you think? Uh-huh.
Like 1 through 8.
Okay, so we could use 1 through 8 and 9 and 10. Did anybody come up with anything else? Okay, I agree. That makes the most logical sense to me. So on our random number generator, in a minute, we're going to use numbers 1 to 10. 1 to 8 are going to represent she makes it. 9 and 10 are going to represent a miss. And so we need to simulate what actually happened, which is these 50 free throws. So twice, you are going to simulate 50 free throws. And what you care about is what proportion did she make. Are we using replacement? If I get a 1, can I get a 1 again? What does that mean? A 1 and then another 1. She made it again. Okay, let's real quick review how to do this on your calculator. What you are doing right now is you are doing 2 different samples of size 50, calculating a sample proportion for each. When you're ready, you need to come up here and put a dot where those 2 belong on the dot plot. My pen is up here. Just write on my iPad and put where your dots go. Okay, so here's what we got. Here's our simulation. You don't need to copy this down. If you want to take a picture, if you just get the idea of it, that's fine. Okay. So let's keep going. What does each dot represent? Each dot in this case is 1 random sample of 50 free throws. And specifically, we are looking at the proportion of free throws made for that sample. One thing that's really interesting, I think, about our dot plot, before we did this, where would you have expected the center of the dot plot to be? What do you think the most common number or proportion would have been if she's an 80% free throw shooter? 0.8. We would expect the center to be 0.8, and maybe it is because of these two unusual ones. But to me, it's really unusual that 0.84 and 0.86 are so common. Okay, here is the key to this. For an 80% free throw shooter, what is the probability that a sample of 50 shots ends with 64% or less free throws based on the dot plot? Okay, so if we look at that on the dot plot, 64% or less, so that's here, and we'll notice that happened twice. So what is the probability? Well, it happened 2 out of however many samples we have up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I counted 37. Doesn't really make sense. It should be an even number, but let's assume that I counted correctly. So 2 out of 37, whatever that ends up being. Can somebody divide that for me, please? .054. So 0.054. Now, some things I want to talk about. You may be wondering, why are we looking at or less? Well, there's 2 reasons. First of all, we don't want to look at the probability at one specific event because that is too limiting. We're looking at an area. And the reason it's or less is this follows the direction of our alternative hypothesis. So if we go all the way back up here, alternative was less than. That's why we're looking at R value and less than. So that's why we're looking at less than. This .054, if you watched the videos and did the reading, this is called our p-value. P-value standing for probability. So it is the probability of getting the sample we got if the null were really true. If we were to interpret this or put this into words, we would say, assuming HO is true, so assuming she really is an 80% free throw shooter, there is a 0.054 probability of getting a sample proportion, a p-hat, of 0.64 or lower just by chance. So even if she's an 80% free throw shooter, she would get a sample proportion of 0.64 or less just by chance. Okay, and then here is the key to everything, is what does that mean? So what does that mean about, is she an 80% free throw shooter or not? What do you think we're going to compare this number to? What do we normally compare it to? 0.05. Okay, so Mr. Wilcox is claiming she's less than an 80% free throw shooter. Do we, in fact, have evidence to support his claim? No. So what you're going to do is we are looking at our number is greater than 0.05. So no, we do not have evidence or have significant evidence to support Wilcox's claim because a sample proportion of 0.64 when p is 0.8 could happen by chance alone. That is the layman's term, bless you, for this question, but we need to put it in terms of stats terms. We are not saying that she's an 80% free throw shooter. We are saying we don't have enough evidence that she's not. Okay, so if you notice the way that I worded it, I said we don't have enough evidence for the alternative. We don't have enough evidence for Wilcox's claim. And so the question is, how do we put that in terms of stats? You are always going to show this. So we are going to say because that 0.054 is greater than 0.05. The way to say we don't have enough evidence is we say we fail to reject the null as, and now we're going to say what that means in words. What that means is we don't have enough evidence for Wilcox's claim. As we do not have sufficient evidence that Mrs. Gallus is less than an 80% free throw shooter. Symbolically, we don't have evidence or enough evidence that P is less than 0.8.
What if we're doing a question like this and it's equal to 0.05?
Theoretically, it shouldn't be.
Okay.
It'll always be a little bit bigger or a little bit smaller.
Mm-hmm.
Generally, we do this strictly as greater than. So theoretically, if you got 0.05, that is not, that we would reject. That's another question because it's not bigger. Okay, here's what we're going to do. We're going to write down a few more notes. You're going to do an example, and then we will take our break. Sound good? Okay, next page, the box at the top. There are two things that you were supposed to get from this. The first thing, so the first learning target, is how to write the hypotheses. Our hypotheses are always in terms of a parameter. So it might be population proportion, it might be population mean, it might be population standard deviation, but it always has to be a parameter, not a statistic. The null, which we denote by HO, will be some parameter, so in this case we did proportion, equals some value. It's always going to be an equal sign though. So the null will always be an equal sign. The alternative, which we denote by HA, is the same symbol, but it's going to be an inequality. It'll either be greater than that same value, less than that same value, or not equal to that same value. And there are terms for each of these. Greater than is called an upper-tailed test. Less than is called a lower-tailed test. And not equal to is called a two-tailed test. So that's the first thing that we have to be able to do, is we have to be able to write a null and an alternative. second thing we have to be able to do is we need to be able to write a full conclusion. Like a confidence interval, the conclusion has 2 sentences. Hypothesis test, there's also going to be 2 sentences, the last 2 sentences from the previous page. The first one is we have to be able to interpret a p-value. The way to do that is we're going to say, assuming HO is true. And then you're going to say what that HO is. P equals, mu equals, so on and so forth. There is a then you're going to plug in what your p-value is, so what that probability actually is. There is a blank probability of getting a, right now it's going to be p hat, but it might be x bar, it might be a different statistic, of blank, whatever we got, or more extreme, purely by chance. So that is the p-value. And then what does that mean in terms of a conclusion with reject or fail to reject? So that's what we're going to do next. In the case that we did, because our p-value was greater than alpha, which we'll talk about, alpha we used was 0.05. We failed to reject the null, as we do not have convincing evidence for HA, of course, in context. Now, that is the sentence for failing to reject. In blue, I'm going to write what you would do if you reject the null. If you reject the null, your p-value is less than normally 0.05. So if you end up with a really small p-value, you're going to say that we reject the null, and we do have convincing evidence for the alternative. Questions for me? Okay, here is the problem that you are doing. I'm changing a few things though. Fascinate.com claims that 84% of teenagers think highly of their mother. To investigate this claim, a school psychologist selects a random sample of 150 teenagers and finds that 132 think highly of their mother. Do the data provide convincing evidence that the true proportion of teens who think highly of their mother is greater than 0.84? Here's what I want to tell you real quick. Part number 1, it says state the appropriate hypotheses. That's the null and the alternative. When it says define the parameter of interest, that's P in words. So P is the true proportion or population proportion, blah, blah, blah. And then the other thing is in question 3, we're going to change this p-value. I want it to be 0.032. 0.032. So I want you to take, I don't know, 6 to 7 minutes to do all 4 parts with the people around you, and then we will go over this. So if you can look up here, here is the answers. Okay, your null, it always needs to be a population, in this case population proportion, same symbol. The null will always be equal to, and it's whatever the claim is. It's not the sample, it's the claim of that 84%. A proportion though is between 0 and 1, so it should not be written as 84%. It should be written as 0.84. And then like I said, when it says define the parameter of interest, that's P. You can see the parts that are underlined that are most important. You either need to say true or population. You have to say proportion. We need to refer to all teens, and this has to be done in present tense, not past. And then the greater than is what brings us the alternative. So is there evidence that P is greater than 0.84? Yes, because we got a sample proportion bigger than that. So then interpreting the p-value, assuming our null is true, there is a 0.032 probability of getting a p-hat of 0.88 or greater, just by chance. And then here is our conclusion. Our p-value is less than alpha, which means we reject the null, and we do have evidence for the alternative. That needs to be put in words, though. So we do have evidence that p is greater than 0.84, but what is p? P is the true proportion of teens who think highly of their mother. One thing I want to point out to us, we have not proven that the true proportion is greater than 0.84. We have evidence, that's it. We've proven nothing. If we fail to reject the null, we still have proven nothing. Okay. The vocabulary here is incredibly important. It is very important that we reject the null or fail to reject the null. There is nothing else that I will accept. If you talk to people in a college stats class, sometimes college stats classes accept other vocabulary. We will not. Questions for me? If you could now go back to the note packet and find this part B. This is, it was page 6, but I think you put the activity into the packet, so that shifted things around a little bit. But I want to take like, I don't know, 9 or 10 minutes and write down a few last things. We're going to skip around a little bit. We're not going to fill out all of this. I just want to write down the things that are most important. Did we find this? Okay, great. First thing I want to just make sure that we all are clear on is what the possible conclusions for a significance test are. The first one, if you end up with a p-value that's small, we will reject the null. That means that we have convincing evidence that HA is true. But of course, you would say that in context. If you end up with a p-value that is large, what we mean by that is that your p-value is greater than alpha. We will fail to reject the null. There is not convincing evidence that HA is true. A lot of the time the analogy that's made here is in a court case. if someone is being tried for something, if we reject the null, so when you go to court, if you're being tried for something, the null, the assumption when you're walking in is that you are not guilty. And we are looking for evidence that you are guilty. So if we reject the null, if we reject that you are not guilty, that means that you were found guilty. If we fail to reject the null, there's not enough evidence to show that you were guilty. The decision is that you are not guilty. In a court case, they will never say that the person is innocent. Not guilty means there's not enough evidence to show that the person is guilty. In terms of a hypothesis test, if we fail to reject the null, this does not mean we have evidence for or that we believe the null. The null is our initial assumption, but we will never say we have evidence for the null or that we believe the null. It's always we have evidence for the alternative or we don't have enough evidence for the alternative. That's it. So again, think of it like you can never say that someone is innocent. It's just that there's not enough evidence to say they're guilty. Okay, most common mistakes that students make. The first one is they forget context. The second one is they forget to compare the p-value to alpha. So you actually need to show the p-value is bigger than alpha or less than alpha. Yes, you can do it in your head, but if you write a conclusion without that, you will not get credit. And then the last one is that people accept or believe the null. They will say things like, I failed to reject the null, so I believe the null. Or I accept the null. That's not true. And this is why I'm saying, if you have friends in college stats classes, a lot of college stats classes, they don't say fail to reject, they say accept. We accept the null. That's not the case. It's not the case. Okay, here is the thing I want to make sure that we understand. If we fail to reject the null, we are saying that the null value is only one plausible value for the parameter. This relates back to a confidence interval. So if we fail to reject the null, we're not saying that that null value is true. We're saying it's plausible, that if we were to construct a confidence interval, that that's one possible value. It doesn't mean that it's the true value, though. Okay, a significance level. That is what I keep labeling with alpha. A significance level is the boundary between what we consider a small and a large p-value. So a lot of times it's 0.05. We say anything less than 5% is considered a large p-value. That's normally the case, but that's not always the case. Okay, and then one last thing I want to write down. Last thing is on the next page. What should be considered when you are choosing a significance level? a statistician will consider the consequences of making a wrong decision. Because like I've continued to say over and over again, we haven't proven anything. We have evidence. In the case of a jury trial, what does a mistake look like? Like in context, what would be a mistake that was made in terms of the decision at the end? There's two of them. What's one?
Guilty or not guilty?
But what is the mistake?
You imprison a innocent person?
Okay, one mistake is you imprison an innocent person. What's the other possible mistake?
Don't impersonate a guilty person.
Okay, you let a guilty person go free. Would you say that one of those is worse than the other? A lot of times it depends on context, right? If somebody's being tried for murder, I don't want to let them go free, right? Okay, so that's what we will be talking about next class, is what do these wrong decisions mean and how does that affect our test?